welcome back to the Wireless Channel. We have one more talk today by Marco on another work done together with Emil Björnsson from the Royal Institute of Technology in Sweden, KTH. And this one is about beyond diagonal reflective intelligence services. Marco, please go ahead.
So hello, yeah, my name is Marko Fidanovski, and I will be presenting this work titled Reciprocal BD-RIS, Scattering Matrix Designed via Manifold Optimization. And again, this work was done as a collaboration between Constructor University and KTH Royal Institute of Technology. So I will begin by giving a short introduction. So next generation wireless networks demand advanced signal processing capabilities while also keeping the costs low and ensuring ease of the deployment. So as a nice figure, I borrowed this one from Professor Emil Björnsson, which he gave during a tutorial for Globecom in 2021, where we have this sector antenna, and then we have two different users. So one is denoted as a fortunate user, and then one is denoted as an unfortunate user. And now the whole point of RIS is that while this fortunate user is able to get a strong signal because of the direct line of sight between the sector antenna and the user itself, this unfortunate user, however, is not able to get such a strong signal. And then we are finding a way to actually be able to give this user as well a fair signal. So one way where we could do this is where we can employ this so-called RIS structure or reconfigurable intelligence surface in this red part here, and then we can sort of engineer the propagation environment to engineer the propagation path of the signal so that it reaches the user with higher power. So when we talk about RIS, we talk about a passive surface. What that means is that this surface is built out of individual elements or passive circuits, which actually filter and then re-radiate the incoming signals without necessarily amplifying it. And what this reconfigurable part means is that we can actually control this propagation, control this property of each circuit. And then, of course, the RIS itself is pretty low cost, which means that we don't actually require any additional active RF chains. So conventionally, this RIS was thought of as like a diagonal structure. What this means is that the scattering matrix of the RIS itself, if we think about it as a matrix, is a diagonal matrix where each element is corresponding to a phase shift, which would be implemented by this RIS. And as an extension to this, we get the beyond diagonal RIS, which in turn extends the degrees of freedom we have to play with this, to manipulate this incoming signal. And then not only can we now change the phase shift of the incoming signal, but we can also change the amplitude. So that's how but how BD-RIS has been implemented. And some fundamental gaps between prior work and the work we have done in this paper is prior works often consider non-reciprocal structures. So what this means is the scattering matrix that we talked about has two constraints, mainly which stem from the physical properties of the RIS itself, which are the symmetry constraint and the unitary constraint. Now, it should be noted that non-reciprocal structures are physically possible. However, they come at a very high hardware implementation cost. So yeah, there are also works which implement such reciprocal structures with the symmetry constraint enforced. However, it should be noted that most works focus on using auxiliary variables to implement this symmetry constraint. And that's where we come and then propose a simple manifold optimization framework for the design of the scattering matrix of a reciprocal BD-RIS, where we formulate this optimization problem, which lets us directly work on the scattering matrix itself and impose the constraints directly on it. So to this extent, we consider the following system model where we have an antenna base station seen on the left-hand side, which is used to serve K single antenna users with the help of a R element BD-RIS. And now for sake of simplicity, we consider that this direct line of sight path between the base station and the user is blocked so that the communication between the base station and the user is facilitated through the to the use of the beyond diagonal RIS. So to this extent, we will now talk about which connectivities of the BD-RIS we consider. And first off, we consider the simple single connected case. What this means is that it's basically the conventional D-RIS where we have a diagonal matrix where we fulfill the constraint that all of the off-diagonal elements are zero. So this means that inherently we have a diagonal structure, and then we fulfill the unitary constraint as seen in equation 2. And furthermore, we consider a more generalized version, which is the group connected BUS. What this means is if we have blocks of uh, we have a block diagonal structure where each block corresponds to one grouping of the BD-RIS, and then we denote this grouping or the number of elements in this grouping as RG, where for a reminder, R was the number of reflective elements and G is the number of groups we have. So each group is interconnected, so each element within each group is interconnected with each other, but no other intra-group connections are available. And then each group has to fulfill the symmetry constraint and the unitary constraint. And then finally, we consider the fully connected BD-RIS where we have a full matrix and we fulfilled the following constraints as seen in equation 5 and 6, which are also the symmetry and unitary constraints. And having defined the scattering matrix and given a beamforming matrix, we assume perfect channel state information, and as such, we can denote the rate as seen here, and then we can write the SINR expression as given in equation 7, where in the numerator we have the signal power, and in the denominator we have the interference plus noise term. Having defined the SINR, we can then formulate our corresponding sum rate maximization problem, which is now dependent on the beamforming matrix and the scattering matrix as well, where this A corresponds to different group connectivities that we have. So we maximize the sum rate subject to the constraints given. However, as the title says, we only focus in this part on the scattering matrix design. As such, we can fix the impact of the beamformer, and as such, we can rewrite the received signal as in terms of a vector form, where we now denote this RHRX matrix as the matrix, which is a concatenation of all of the channels from the RIS to the users. And then simply we can denote the equivalent channel as seen here in E as a concatenation of all of the channels, namely the receive channel, the scattering matrix, and the transmit channel. So yeah, having denoted the equivalent channel, we can now write the SINR in terms of the equivalent channel as seen in equation 10. As we said before, we fixed the impact of the beamformer. As such, our optimization problem now boils down to only being dependent on the scattering matrix itself. So we rewrite it as seen in P2 here, where we have both of the constraints, namely the unitary and the symmetry, seen in equation 11, B and C. So now we have to think about how we can solve this efficiently for all the different connectivities that we have. And the solution to this that we came up with was the group connected BD-RIS architecture. As it's the most generalized version, it can provide a generic solution to the previous optimization problem. And for the number of groups, the group connected case can be boiled down to either a single or a fully connected case. As such, yeah, we have the solution. We have the problem formulated as seen in P2A. Now, for simplicity, we denote the sum rate over all users as this eta, where eta k is simply the user achieved the rate achieved at user k, and then we form our optimization problem as seen in P3, where now we have sort of removed this symmetry constraint, and instead we enforce it through this penalty term that we see here, where this nu here is a non-negative real weight, which and then we have this Frobenius norm term, which is a quantitative measure of how far from symmetric our matrix actually is, and it's added as a penalty term to the objective function. And now we can simply note that equation 14b is recognized as a Stiefel manifold constraint, and as such, we can form our manifold optimization framework given our objective function and the constraint of unitarity seen in equation 14b. So, inspired by this manifold optimization approach, we know that a manifold is locally resembles Euclidean space, and as such, we can apply optimization methods which were derived for Euclidean spaces to this problem here. As such, we can actually, and this problem can be solved numerically using MANOPT. However, we know that the computational complexity of this would be very high, and as such, we in turn derive our own CGA method, which stands for conjugate gradient descent method. So, in order to solve for the general case that we considered, namely the group connected, we begin by denoting the groupwise SI in our equation as seen in equation 15. Now, it should be noted that we can group our thetas like this because, as we said before, each group has only connections within the group itself, but not outside the group. So this is fine. However, having the consideration of each group for the channels themselves is an approximation only, and it's we have tested this, and it's a lower bound approximation. So in turn, when we maximize the sum rate, we are maximizing the lower bound. As such, we can define our equivalent channel for the group connected case, and then rewrite it as seen in equation 16. So having denoted everything in terms of groups, we can now find the gradient of our um, sum rate equation in terms of each group of the theta. As such, we obtain our closed form gradient from the equation 17. However, we don't provide in the slides actually the full closed form gradient so that we can maximize visibility. But for interested readers, we refer them to our paper, which was recently submitted to Transactions on Wireless Communications, and our preprint is also available on arXiv. I will show also a QR code for this uh, at the end of the presentation. So once we have obtained actually our closed form gradient, we can then follow a simple conjugate gradient ascent method. And then once we obtain the scattering matrix from the subjective function that we have now, which we then project it using the unitary symmetric projection proposed by the corresponding authors, which I have cited in this paper here. So for a clear understanding of the algorithm, I will give a rundown of the actual algorithm itself. So in the beginning, we begin by initializing our initial theta as a random block diagonal unitary symmetric matrix. What this means is that we have a block diagonal matrix, and then each group or each block of the block diagonal structure is unitary symmetric. We then compute the initial objective function as using the equation seen here in the blue part, and then we compute the Riemannian gradient using this tangential projection operator, which is basically a function of the Euclidean gradient and the theta itself. We then set the initial search direction to be the negative of the Riemannian gradient, and then here from step 3 to 15, we begin our CGA algorithm, where in step 4 to 6, we actually check if the ascent direction in this sense is a correct direction. And then in step 7, we compute this new theta. So in the iteration, we compute a new theta using the Araminko line search algorithm, which computes a term alpha, which is then used to update the theta as a function of a retraction operator, which is given here in the blue, where the alpha is here seen here, and then the theta we have here, and then psi is our ascent direction. So once we have our updated theta, we then compute the new objective as seen in step 8, and then we compute the new Riemannian gradient. Then this beta here denotes our conjugate gradient momentum term and is computed as seen in step 10, and then we update the direction. And then we just iteratively do this until we reach convergence. So after we, as I mentioned before, after we do the CGA algorithm, we then project it using the method I mentioned before. So we extract the groups from the full theta, then symmetrize all of them, perform an SVD on the symmetrized version, and then use the left and unitary symmetric matrix at the end. And then we assemble the full theta, which is now the optimal theta as a block diagonal of all of the group. And for convenience, we have shown here the convergence behavior of our proposed algorithm, where intuitively we can see that for different group connectivity, so as the order of complexity grows, so does the number of iterations required for convergence. And we will now begin by showing a bit of simulation results. But first, we talk a bit about the complexity. So for convenience, I only talk about the complexity of the proposed algorithm, and it can be seen here for the different connectivities, where I is our number of CJ iterations, and then L here is the number of Armijo line search iterations. And then regarding a simulation setup, we consider IID Rayleigh fading channels for the transmit and the receive channels. And then we assume that our system is operating at a 2.4 gigahertz, at a range of 2.4 gigahertz. And then we assume that each user has identical noise power, which is given by minus 80 dBm. We also consider a distance-dependent large-scale fading model, as seen in the equation here, where we have the different parameters listed below. So moving on, we can start showing simulation results. First set of results we have is the CDF of the summary performance of our scattering matrix, of our optimized scattering matrix. So it should be noted here that the beamforming metric used is the same. So we use the same beamformer for both scattering matrices. And then our state-of-the-art benchmark is this paper that I have referenced here. And the main thing that should be noted here is that our proposed algorithm, or our proposed scattering matrix, outperforms each of its equal grouping of the state of the art, while also it should be noted that for the single connected case, we reach the performance of a group connected architecture with a group size of 2. So in this sense, we beat or we approached the performance of a magnitude of order higher connectivity, where we consider the order to be 2. Here, this is a bit of a dense slide, but in the first row, we showcase just a single, just the performance of the proposed scattering matrix against the state of the art. So in figure 1, the proposed scattering matrix, we only consider the single connected case, and we compare it against the state of the art single connected and group connected side with a group connected case with a group size of 2. In the second figure, we compare the proposed scattering matrix of both group connected cases, so group size 2 and group size 4, against the same state-of-the-art architectures. And then in the last figure, we compare the fully connected cases for both. The second row here, we showcase different beamforming, or the effect of different beamforming on our proposed scattering matrix. So yeah. And then finally, we showcase the sum rate performance as a function of the number of reflective elements, where all of the constraint, all of the conditions are the same. So we consider a fully loaded system where we have 5 transmit antenna base station with serving 5 single user antennas, and then we take this result at a maximum transmit power value of 20 dBm. So this was the last figure that we have. Thank you for your attention, and if you have any questions, I would be happy to answer them. Here on the left side, we have the link to the archive of the preprint that we have posted, and then here I have referenced Professor Bjornson's YouTube channel.
Thank you very much, Marco. Any question, guys? If not, I have one always. Um,
Yeah.
Let me first try to summarize in a sentence what is really going on here. And what's really going on here is that after you formulate your problem, you make it so that the reciprocity is put as part of the objective with a regularization term, new,
Mhm.
and you solve the problem on the Stiefels manifold to enforce the other side of it, which is the unitarity of the blockwise scaling matrix design, correct?
Exactly. And then we
Okay.
project it just to further enforce symmetry and unitarity.
Yeah, I have one more sentence to summarize, and then very central to the whole thing is that this allows now for the computation of a closed form gradient, which then is used with a gradient ascent algorithm to update iteratively the scattering matrix exactly if you go back to
Yeah.
the exactly, meaning that in principle one could also attempt to do that without computing the closed form gradient. And here comes my first question: what
Mhm.
is the complexity gain that you obtain by giving this gradient in closed form as compared to doing it numerically? And of course, I'm not asking you in order of magnitude or notation. I'm
Mhm.
asking your observations in simulations. How big a system, for example, can you handle with the closed form as opposed to if you were had to do this numerically?
So yeah, thank you for the question. Of course, we mentioned that this could be also done numerically. However, it's very computationally heavy. For example, if we try to plot the figure here on the top left side, using our proposed algorithm, this would take maybe around a minute maximum. But if we were to do it using the numerical operation, then it might take several hours, maybe even a day.
Okay, so it's very crucial to the contribution that
Yes,
the closed form of the gradient was given. Now I have a
of
curiosity
course.
actually, which is that now if you go back to your objective, you still have your rate function there, which is not convex, right?
Yeah.
So I wonder how you were able to just do a gradient ascent on this. I mean, don't you try? Didn't you look at all? Or wouldn't it make any sense or give any further advantage to convexize the first term of the objective in 14a? For example,
Well,
using some
one
fractional programming or something like that?
Well, the objective term actually, I mean, when we compute the gradient, right, we obtain an equation which is still
Hmm.
inherently not convex, but we can still use it. We just compute what this means when we compute the initial objective is we just obtain a value, right? So it's not like yeah, I mean, I would have to look into this maybe a bit more, but to my understanding, it does not matter.
Well, it of course you always will reach just a local optimum.
Yeah.
The advantage of doing some regular majorization methods such as fractional programming is that you increase the likelihood that your local optimum is closer to the global optimum, right? Because
Yes.
it's in a way it sort of paces your optimization, yeah. So actually,
Mhm.
this is good news because that means that if you just apply a fractional programming method on the log part of your objective, because the other part is okay, right?
Yeah.
Yeah, you might even have a slight further gain, and it would also likely simplify the expression of the closed form of the gradient.
I see.
We
Yeah.
might
Okay.
want
Yeah.
to take a look
Yeah.
into that. Now, one last question. I apologize for asking so many things. You have this regularization term in U here. So if I read it correctly, if you set it to zero, you go back to a diagonal case, right?
I go back to a non-reciprocal case.
Oh yeah, yeah. So sorry. Yeah, yeah, yeah,
Yeah.
yeah. You go back to a non-reciprocal case. So I mean, in other words, this method also would work for a non-reciprocal RIS design.
Yes, in theory, it should work. Yes.
Okay. All right. Thank you very much. Anybody else? Any further questions? Comments?
I think the numerical results are really interesting because you are showing very large performance variations between different curves, which is I generally find interesting. I mean, one first reflection is that just for the same setup, this proposed scattering method design is beating this state-of-the-art method, which is interesting on its own. That apparently that one wasn't particularly good. But my question is, do you have any feeling for why there is such a big gap between the single connected case and the fully connected case? This seems to be a case where beyond diagonal risks is really shining, but why is that?
So thank you for the question. Actually, this is a very good observation. And if I remember correctly from your webinar that you gave a few days ago, you had a case where you consider a Rician fading channel, and then for a differing Rician factor, you would see that actually the single connected or the conventional RIS reaches the performance of a BD-RIS. But I think that this is also a function of the channel we consider, or of the channel model or the system model. So in this case, we consider multi-user MISO. So maybe that's also a contribution as to why this gain is so different.
Mm. Yeah, no, so just looking at the numbers here, my impression is that the single connected case is probably multi-user aspect here doesn't work particularly well. It might be that just scheduling one user at a time would give similar performance because you have an almost 5 times improvement from the single connected to the fully connected case here. So it could very well be that the BD-RIS is able to really do what we wanted to do, to take signals from the base station and spread them into 5 different beams, while the single connected case cannot do that at all, and therefore it just creates too bad channel matrix.
Yes, exactly. That's a very good observation.
I think Emil answered the question. That's
Yeah.
exactly the point. BD-RIS is supposed to have a lot more degrees of freedom in how it engineers the channel, as you said in the beginning. Marco paraphrasing Emil's also last talk. But that really is a function of how you optimize the coefficient. So if the job of optimizing the scattering matrix is not done right, then you still can reflect things to multiple directions, but they don't go exactly where you want. And that's exactly what happens, right? So you need to be careful now. Once you have this new gun, which is the ability to reflect in different directions, you need to control the gun and point it to the right places. And I think that this is pretty much what we are finding here, that doing a very good, careful, high-performing scattering matrix becomes essential to properly exploit the potential of beyond diagonal matrices. Thank you very much, Emil and Marco, for the discussion. Anybody else? Any other questions or comments? If not, thank you all again, and yeah, we can close this session now, and I see you guys again next time in the Minus Canon. Okay.